Hello, this is lesson number 10, Electric Fields, the beginning of chapter 11. So, I want to remind you of a few things from Physics 20 before we get into the field stuff, and it means that I want to talk to you a little bit about forces. You might recall from Physics 20 that we kind of break up forces into two categories almost. There's contact forces, and that is like the most basic of I want to push something out of the way, so I push it with my hands. You actually have to be in contact with it. It means that we're looking at a situation where there is a physical connection between the two objects. It doesn't even have to be the two objects themselves touching. If we have like a rope tied between two objects and one's pulling on the other, that counts as a contact force because the rope itself then is a point of contact between the two objects. But the other category, action at a distance, is almost a bit more mysterious because that's things like gravity or magnets or electrical charges. Because in those cases, things don't need to be touching in order to be pulling or pushing on each other. Think of the example like the moon orbiting the Earth right now. The Earth is pulling on the moon with the force of gravity. And by the same token, the moon is pulling on the Earth. That force of gravity is the reason why the moon continues to go around the Earth. If there wasn't this non-contact action at a distance force, there'd be no reason for the moon to continue going around us. It would just spin off into space. Contact forces tend to be easier to understand because we can see objects touching, but action at a distance is a bit harder simply because we do have to recognize something is happening that is not a measurable touch, but still involves some of the fundamental forces of the universe. Now, Michael Faraday is a person who's trying to figure all of this out while playing around with the idea of electrical charges in his head. And the story goes that he was walking along, very good British thing to do, go for a walk, and he was walking past a farmer's field when he noticed that because of the furrows that had been cut through the soil, I guess they were getting ready to plant or whatever, you could do something like pour in a whole bunch of water at one end of the field and it would flow over to the other end of the field. Even though the two ends of the field didn't touch each other, there could be an interaction across the field. And that's where we get the word field from. And that's what we're supposed to picture when we think of electric fields, magnetic fields, gravitational fields. This idea of an area that surrounds something and that it's almost like it has these invisible tendrils that go outwards and can either pull or push on things that are nearby it. The other phrase that's sometimes used for this is sphere of influence, which I know sounds more like we're talking about something from social studies class, but it's still valid here. It's still this idea of when you're closer, the effect is stronger. When you're further away, the effect is weaker. Now, there are two kinds of fields, scalar fields and vector fields. Scalar fields, the best example I have for you of that at a high school level would be temperature that you measure when you're near a fire. So you could be standing near the fire and the temperature registers 41 degrees Celsius. But you go further away, the temperature maybe drops to 28 degrees Celsius. Now, that's showing that you're within the sphere of influence of the heat being given off by the fire, but it's scalar because if it's temperature, I would not say something like 41 degrees Celsius east. That just doesn't make sense. It's just 41 degrees Celsius. But a vector field has direction. So think about the gravitational field of the Earth. If you drew a diagram from Physics 20 showing the gravitational field of the Earth, you would draw a bunch of arrows pointing inwards towards the center of the Earth. That's the gravitational field of the Earth. It has a magnitude, it has a strength at the surface, 9.81, either meters per second squared or newtons per kilogram, but it also has that direction, pointing towards the center of the Earth. Now, for electric fields, Faraday basically says every charge has an electric field, whether it's positive or negative, and that if we put charges next to each other, it's the fields that touch. It's the fields that interact and allow those forces to be experienced between them. Now, it's important to note here that the field is not a force. It just exerts a force. It's sort of like if you're pushing a desk across the floor, I'm not going to say you are a force. You're a human being, but you can exert a force. Think of it the same sort of way for fields. Fields themselves are just a way for us to visualize using a model that area of influence around a charge, and that if other charges are put in that area of influence, they will experience forces. So, how are we going to detect these electric fields that exist around charges? Well, Faraday said we should put a little charge nearby and just watch how it reacts. That test charge, because that's what we're going to call it, because it's testing the electric field, has to have some particular characteristics, because it will, since it is a charge itself, it will have its own electric field, and we want to minimize its effect to kind of like warp the electric field of the charge I'm measuring for, which, by the way, we're going to refer to as the source charge, because it's the source of the electric field I'm measuring. So, for a test charge, we'll think of them as being this mathematically perfect point in space where this little individual charge exists. And it has to have the characteristics of being positive 1 over infinity charge. Now, that might sound kind of weird to say, but there's reasons for why we're saying it. First of all, we're going to always say our test charge is assumed to be positive, unless we're told otherwise, because that way we'll always give a consistent direction to the electric field that it's measuring. We also will say that it's 1 over infinity coulombs of charge, because 1 divided by infinity is a number so close to 0 that it essentially becomes 0. It's 0 coulombs of charge, which means it won't have a measurably significant electric field of its own. Now, of course, a charge that small is impossible, and we can actually, in problems, make the test charge any value we want, but we'll assume that it is such a small charge compared to the source charge that it's not having an effect on the field produced by the source charge. It's kind of like using me as a human being as a test mass for the gravitational field of the Earth being the source mass. My mass is so insignificantly small that even though I do have a gravitational field of my own, it is so puny compared to the gravitational field of the Earth that it's mathematically unimportant. I don't create a gravitational field that will change the measurement of the Earth's gravitational field. It's basically the same thing that we're saying with test charges and source charges. So, in my diagram here, I'm showing, first of all, if I put a test charge, the little red charge, near a positive source charge, it would want to move away. No matter where I put that test charge, it's always going to move away from a positive source charge. That's why I drew this vector arrow here. That's the direction not only of the electrostatic force acting on the test charge, but by definition also the direction of the electric field. And notice over here for electric field, I'm using the symbol E, but I'm actually drawing the vector arrow above it, and that's because we have to do it when we're talking about electric fields. It's not optional. If we just wrote a letter E, it would mean energy measured in joules, and that's not what this is. And we have formulas in this chapter in physics where we have to actually sometimes have energy and electric fields being measured at the same time, so we need to make sure that we're not confusing them. In this diagram, I'm showing a negative source charge, and because electrostatically the force would be pulling it in, that's also the direction of the electric field. So around a positive source charge, the electric field points away, and near a negative source charge, the electric field points towards. We're going to be doing stuff in a later section, a lot more about drawing diagrams to represent this, but for now, that's what we need to know about the direction. So, in my first example, I tell you that I have a steel ball that has an unknown charge on it, and I'm treating it as my source charge. It's either positive or negative, but I don't know. I take my test charge and I put it down to the right of the source charge. And I watch as the test charge is moving away on its own. It's being pushed to the right. I want you to identify if the steel ball is positive or negative and explain your reason. So pause the video for a moment if you want to draw a diagram of this or something and try to reason it out. Okay, so what we should be looking at here is that because the test charge moved away to the right, the only reason a positive test charge would move away from that source charge is if the source charge itself is positive. So with the test charge always assumed to be positive, unless there's something very specifically told that makes me think it's got to be something different, a positive test charge would be pushed away by a positive source charge. The steel ball is positive. Now, Faraday also gave us a formula for measuring electric field strength. And notice right here in the formula, the E does have that vector arrow above it, which is mandatory for you to write. You can't skip the arrow. And he measures it as the electrostatic force acting on a test charge. So that's why it's Fe over Q on the other side. Now, one of the problems that we're going to have is just simply remembering that the Q, the value of the charge in this formula, is the test charge, not the source charge, because we're going to have questions where we'll know stuff about both of those charges. So what we should be doing is actually trying to draw a parallel between this and something we did in Physics 20. Because look at this formula next to our formula for the standard basic formula for gravitational field strength. Both of them are measuring a field that is equal to a force acting on a test. So in the gravitational formula, we're measuring gravitational field strength based on the gravitational force that a test mass feels. Remember, back in Physics 20, when you were putting a mass in this formula, it would have been a desk or a car or a person or an apple. It was never the mass of the Earth you put here. You were always putting the test mass here, not the source mass. It's the same idea over here. This Q, when we're measuring the electric field that causes an electrostatic force to act on a test charge, again, this is now a test charge because it's not going to be the source charge that is creating the field. So that's a way to remember which one's which in this formula. So if I look at an example using this, I tell you that I have a 3.7 Coulomb test charge that is 2.7 meters to the right of a negative 7.94 Coulomb source charge. If there's an attractive force of 3.62 times 10 to the 10 newtons acting on the test charge, determine the field strength of the source charge at that location. Now, I know you should look at this charge, 3.7 coulombs, and say, there's nowhere near that being 1 over infinity coulombs of charge. What kind of a test charge is this? Well, remember, I can make it any charge I want. Typically, what we will see is that it is smaller than our source charge. And that's all I really have to worry about. I'm just going to pretend that a object with a charge of positive 3.7 coulombs is close to infinity small. I know that's impossible, but that's just the way we're going to use it. The important part here is I've got the force that the test charge is feeling. That force has to be this electrostatic force. But then I do have to remember which of my two charges go on the bottom here. It has to be the test charge. There's nothing about the 2.7 meters that gets substituted in. This is purely just me taking the force that is exerted on the test charge and finding out what the electric field strength is. So I go ahead and I plug that into my calculator and I get an answer. And electric fields, for now at least, are measured in newtons per coulomb. So rounded off for sig digs, I've got 9.8 times 10 to the 9 newtons per coulomb. But I still have to give a direction. If my positive test charge was placed to the right of a negative source charge, would it be attracted or repelled? It would be attracted, which means because opposites attract, that's law of charges. That means that the test charge, which was placed to the right, is going to feel itself being pulled to the left towards the source charge. So the direction of my electric field is to the left, and I have to include that. For example, number 3, I tell you a force of 2.1 newtons is being exerted on a 9.2 times 10 to the negative 4 coulomb test charge when it's placed in an electric field created by a 7.5 coulomb charge. Well, hey, at least this time the test charge is really smaller than the source charge. If the force is pushing it west, determine the electric field at that point. Okay, so I'll just take my numbers and start substituting them in. Again, I'm just going to use the force that's being exerted as Fe and my test charge as the charge that I put for Q, 9.2 times 10 to the negative 4. I go ahead and I calculate that. I get a number that I have to round off for sig digs to 2.3 times 10 to the 3 newtons per coulomb. But here's the important part. If my test charge was being pushed west, whatever the direction of the electrostatic force acting on my test charge is also the direction of the electric field. So west is the direction of my electric field. For example, number 4, I tell you that I have a positive test charge of 3.7 times 10 to the negative 6 coulombs, and I put it in the same place in the electric field as the original test charge in the previous example. Determine the force that will be exerted on that one. Well, this is a pretty standard question that we get asked. We've already figured out an electric field, or it's given to us, and we want to know what the force is being exerted on a charge that we place in that location. Being in exactly that location is important because if I was a little bit closer, the electric field would be stronger. If I was further away, it would be weaker. If I was on the opposite side, it would be a different direction. Like all this stuff I've got to basically take into account. So basically saying it's in the same spot, I get to just take my formula for electric fields, solve it for the electrostatic force, and then put in my electric field from the previous question. And even though I'm just showing 2.3 here times 10 to the 3, I would still use the unrounded number that's on my calculator in my calculations. I put in the new test charge, 3.7 times 10 to the negative 6 coulombs, that's getting shoved around, and I get my answer, which I figure out what it should be in scientific notation, 8.4 times 10 to the negative 3 newtons, but direction. Okay, the previous example, the positive test charge was being pushed west. This test charge, still a positive test charge, would also get pushed west. Nice, easy answer there for that, I hope. Now, for example number 5, I decided to spin it up a little bit. We're still talking about the same source charge as the last two questions. We're still talking about even being at the same location, the same spot in its electric field. The only thing is, now I'm doing something that's a little bit different. I'm going to put a negative 4.81 times 10 to the negative coulomb charge in that spot. Now, this is the weird thing. It's negative, so it's not really a test charge. But I'm treating it as though it's a test charge because I'm placing it near my source charge and I'm trying to figure out what happens to it. So I still take the formula and manipulate it for force. I put in the electric field, and again, I would use the unrounded number for the electric field here. I put in basically the absolute value of this test charge, kind of, and I put it in here, and I just say, how much would that much charge feel as a force? 109.793, which I'll round off for sig digs like I always do to 1.1 times 10 to the 2 newtons. But now I've got to give a direction. I know that a positive test charge was getting shoved west in the previous examples. So what would happen if I put a negative charge in that location? It would get pushed east. So I do have to be aware that if I do put a negative charge as sort of a test charge into one of these electric fields, I reverse the direction of the electric field to give an answer about the direction of the force. The electric field at this location is still pointing west. Because electric fields are based on what would happen to a positive test charge, that's how I know the force is pointing east on a negative charge. Now, this is what we refer to, for lack of a better term, as the other formula for figuring out electric fields. The difference here is that this Q is no longer a test charge. This is the source charge that's making the field. And R, being thought of as like a radius, is the distance measured from the center of the source charge of how far away we are. We have K for Coulomb's constant, and notice here that in this formula, at least on your data sheet, they do show electric field in absolute value bars. What I would just basically say to you is just whatever the charge is that you put in here, just kind of consider whether it's positive or negative, what that would do for attraction or repulsion to a positive test charge to say your direction. That's why they're a little bit worried here and they put in these absolute value bars so that you're not trying to come up with a direction based on left or right for positive or negative charges. You're doing it based on the law of charges and whether you see attraction or repulsion. But we'll see that in the examples in a moment. We can also parallel this formula to a formula from Physics 20 again. You might recall this formula let us figure out the gravitational field when we were talking about a source mass, like let's say the planet Mars, and how far we were from its center. We could figure out gravity there. This is now the same sort of formula for electric fields because we have Q, a source charge, and we're saying how far are we from the center of that in order to get its electric field. So, in this example, I tell you that I have a tiny metal ball that has a charge of negative 3.0 times 10 to the negative 6 coulombs. We're treating that as our source charge. This little metal ball with that charge is the source of the electric field that I'm going to measure. And I want to know the magnitude and direction of the electric field it produces at a point, P, 30 centimeters away. You'll see this a lot in diploma questions. They'll label a location P, a point in space, as P, and they're just saying at exactly this spot, what are we measuring? So for this question, I don't need a test charge because I have the source charge to put up here where Q is, and I know how far away I am from it. And K is just Coulomb's constant. So I start sticking in the numbers, 8.99 times 10 to the 9 for Coulomb's constant. I put in the source charge, but I'm putting it in just as an absolute value because I just want to find out the magnitude of the electric field here. And I was careful to change 30 centimeters into meters by dividing by 100. Don't forget to square it. When I do all of that, I get an answer of 299,666.66666 repeating. I'm going to round that off to 3.0 times 10 to the 5 newtons per coulomb. Now, I don't know if point P is to the left, to the right, above, below, whatever. But what I do know is this. If my source charge is negative, a positive test charge, if I did have one that was brought nearby, would be attracted towards it. No matter where I put that test charge, it'll always be attracted towards that. So I'm just going to give that as my direction, towards the source charge. And that's a perfectly valid way of saying it. Now, what about when we have multiple charges? You knew it had to be coming because we're always talking about stuff like this, right? Even when we were doing electrostatics. So in this example, I tell you that I have two negative charges, 0.58 meters apart. I want to know what the electric field strength is at a point exactly halfway in between them, right in the middle here. So just like when we did stuff previously, like with Coulomb's law, where we can only do so many charges at a time. When we're doing electric fields, we can only say what's happening from one charge at a time, and then the other charge separately. So when I do this question, at first, I'm just going to say, what's the electric field at this point, halfways between the two charges, only created, only generated by my 1.2 Coulomb charge. So I take my formula for a source charge, I stick in Coulomb's law or Coulomb's constant, I stick in the charge as an absolute value, and notice I took the 0.58, which is the distance between both of them, and I divided it by 2, because if I'm in this location right here, I'm halfways away from the blue charge. Stuck in my numbers, got an answer. Don't worry right now for a moment about direction. We'll get to that in a moment. But this is the magnitude of the electric field produced by the blue charge at this point in space right here. Now, I'll do the same thing for the red charge. Again, using just it as the source, and at the halfway point, 0.29 meters away, I stick in all those values and I get this electric field strength. Now what I got to think about is, what would happen if I put a positive test charge right here in the middle? It would be pulled to the left towards this blue charge. So this electric field should be given as a negative value because it's to the left. And the positive test charge would feel itself pulled to the right by this red negative charge over here. So this electric field should be to the right, because we always define the direction of the field based on the direction of the force acting on our positive test charge. So this field is to the left, it's negative. This field is to the right, it's positive. So I'll take the two of them and I'll add them. Here's the negative value, here's the positive value. I add them together and I get a final answer, 2.9 times 10 to the 11 newtons per coulomb. And the direction would be given to the right because it was a positive answer and positive to the right. It basically makes sense. This is a bigger magnitude charge, so its field strength is winning the fight against this one. Now, a bunch of questions for you to try for some homework. Some of the stuff involving double charges making electric fields does start to get 2D-ish. Give those a shot and see what you can do with them. And keep thinking back also to the way that we were doing electrostatics and vectors in the previous chapter. Have some fun with that.